Hey there, guys. I'm just going to go over a quick follow-up on linear factorization, and these two problems are under your lessons. They're example problems under the lessons. So for part A, which isn't really the part I wanted to address, but since it's there, I'll address it anyway. It's going to be a difference of squares. So remember that if you can recognize it, it is the most difficult part of factoring a difference of squares, you can factor it. Difference meaning subtraction of two perfect squares, meaning I can take the square root of each one of them perfectly. So if I recognize that, one is plus, one is minus, I take the square root of each one. The square root of x to the fourth is x squared. So each parenthesis starts off with x squared. And why is that? So x to the fourth, I'm just going to take a sidebar here. So x to the fourth power, a square root is nothing more than a power of 1/2. And when you have a power to a power, properties of rational exponent states when you have a power to a power, you multiply it. 4 times 1/2 is just 2. So that's why each one is squared. And then the square root of 625 is 25. You think you're done, but you're not actually done yet because we have here a difference of squares. So this one can again once be factored as 1 is plus, 1 is minus, x, because the square root of x squared is x, and the square root of 25 is 5. Again, no need to take the square root of negative 25 because it's called a difference of perfect squares. So the minus sign is already taken into account. Now, if you saw the last factoring video, we're kind of stepping it up from algebra. What happens when you have a sum of two perfect squares rather than a difference? Well, that just means that you can apply the same method. It's just that when you square root, it's going to give you 5i rather than 5. So the square root of x squared is just going to be x. And the square root of 25, it's like square root, this is like square rooting negative 25, so that'll give you 5i for each one. One is plus and one is minus. And I go over more of those videos in the other linear factorization, but again, this one is kind of more of a follow-up for part B. So part A though, there it is. If they ask you for the zeros, remember, if it's factored, you can always apply zero product property, meaning you set each parentheses equal to 0. So if I set x plus 5i equal to 0, I subtract 5i from both sides, and I'll get x equals negative 5i. And then just kind of going on the pattern from here, if I set x minus 5i to 0, I'll get x equals 5i. If I set x plus 5 equal to 0, I'll get x equals negative 5. And if I set x minus 5 equal to 0, I'll get x equals 5. And remember, fundamental theorem of algebra tells us that the degree or highest exponent tells us how many zeros we should have, and we do have 4. Okay, so on to part B. Now, when you're solving for the zeros in a higher degree polynomial, you can't factor this one. You would have to use the rational zero test. So the first step of the rational zero test is to take positive and negative, and again, rational zero test is under 2.03, so I'm kind of following up on lessons here. Factors of the constant, which is 108, over factors of the leading coefficient, meaning the number in the front, which is 1. Now, who wants to list all the factors of 108? I'm really not a fan of that part. So what's going to happen here is you have to list all the factors of 108, and then afterwards, rational zero test states that you will plug them in and see which one gives you 0. There's more than one that would give you 0, but you just need one. So unfortunately, sometimes if it's a large amount of factors, like the factors of 108, it could be the first number you choose, but it could also be the last number you choose. So we're going to take another approach for this as well. Look, I pretty much just typed in the entire function given to us and graphed it under Desmos. Now remember, zeros are just another way to say what x equals to, which is just another way to say x-intercepts. They're all interchangeable. Notice that y equals to 0. And when we solve for x algebraically, we always change y to 0. So These are all the same things we're talking about. So I have my answers here so far. X equals -3. Sorry about that. X equals -3, X equals -2, and X equals 2. Keep that in mind. So I know from Desmos that X equals 2, X equals -2, and X equals -3. I'm not writing them in any particular order. This is just how I remember them from Desmos. So what do I do now that I know this? Because there's supposed to be 5 zeros. Remember that the highest exponent degree tells us how many zeros we should have. We only have 3, which means we either have multiplicity or we have some imaginary numbers going on. So what you're going to do here is you can apply synthetic division or long division. I'm learning that you guys prefer synthetic, so that's the route I'm going to take for this particular problem. So what we're going to do here is synthetic division. I am going to put 2 in the box, and I'm going to bring down all of the coefficients, which is 1, 3, 5, 15, -36, -108. Okay, and from here, start synthetic division. Sorry, I cannot draw straight lines. You already knew that. Bring down the 1. Number hits below the line, multiply it by the number in the box. 1 times 2 is 2. Numbers are together, add them up. 3 plus 2 is 5. 5 times 2 is 10. 10 plus 5 gives me 15. 15 times 2 is 30. 30 plus 15 is 45. 45 times 2 gives me 90. We have 90, and the numbers are together, so we add it to -36, which is 54. And 54 times 2 is 108, which works out. We already knew that the remainder, or the number in the end, it was supposed to be 0 because we determined 2 is a factor already. So what do I do next? I use well, we know 2 works, so I use the other 0 now, -2. There's a reason you're doing this, by the way. And we're going to bring down everything that we just used. I am going to be a little lazy here, plus I'm kind of out of room, so again, reason for that. And we're going to use all the numbers we just solved, sans the remainder, and kind of do this again. Bring down the 1. 1 times -2 is -2. 5 plus -2 is 3. 3 times -2 gives me -6. 15 plus -6 gives me 9. 9 times -2 gives me -18. 45 plus -18 gives me 27. And 27 times -2 is -54. So once again, we have a 0 remainder. So from here, I'm going to take these values. And usually I just flip the page, but since this is all one problem, I'm going to erase the previous problem. And I'm going to bring up all those values again. 1, 3, 9, and 27. And test out that last 0 we got from Desmos, which is -3. We're not actually testing it out. We're using this for something. So when I'm dividing, I'm bringing down the powers. So I'll show you what I mean after this last part. So we have -3, which gives me 0. 0 times -3 is 0. 9 plus 0 is 9. 9 times -3 is -27. Again, the remainder is 0. So what I have here is after the remainder is the constant, meaning the number that's by itself. Then each time you move to the left, you add another x. So 0 has an x, 1 has x squared. I'm not actually going to write the 1. So this is what we're factoring. I actually don't need the 0. I mean, you can have it there if you want, but x squared plus 9 is pretty much what I'm solving for, or factoring. And from, remember, part A, this is just a sum of perfect squares, not a difference, but a sum, meaning 1 is plus, 1 is minus. If I take the square root of each one, keeping in mind that when I square root the 9, because it is not a difference of perfect squares, it is a sum, it's imaginary, 3i, 3i. So Remember, we had 3 zeros. We need a total of 5. There's my other 2. I'm going to set each one of these parentheses equal to 0, and I'll get x equals negative 3i and x equals 3i. So I have my 5 zeros. 1, 2, 3, 4, 5. All right. Hope this helps, guys.